Oops. All right, so this is elastic collisions and 2D collisions. Just going to give a little bit of an overview of the lecture we did today. I'll probably go a little quick through this. But basically, we talked about inelastic collisions last time in one dimension. Now we're doing elastic collisions and 2D collisions. Okay. So, how do you know if a collision is elastic? This is like the easiest thing ever. In a problem, you assume it's elastic if it tells you it's elastic, or approximately elastic. Otherwise, don't. Okay. How do you, or if you can determine after the fact that the kinetic energy initial is equal to the kinetic energy final. Otherwise, don't assume it's elastic. Can't do it. How do you solve an elastic collisions? You pick two of these three equations. Momentum initial equals momentum final, kinetic energy initial equals kinetic energy final, and coefficient restitution equals 1. I always pick the first two because they're more versatile. This one works if it's in one dimension only, but so you do what you want to do. But I'm going to exclusively use these two. I think the algebra is slightly easier if you use coefficient restitution equals 1, but a lot of the time I am using a lot of the time I am using Wolfram Alpha to do the actual math for me, so I'm not too worried about the math here. So the nice thing about kinetic elastic collisions is that there's initial velocity of, if you have a collision, there's initial velocity of object A, initial velocity of object B, final velocity of A, and final velocity of B, 4 variables. In the inelastic collisions, you could only solve that if you knew 3 of the 4 velocities. Okay, in an elastic collision, you can actually do it only knowing 2. So let's show that. So 5-kilogram ball moving to the right at 3 meters per second collides head-on with a ball moving to the left. So we've got ball A, 3 meters per second, ball B, 8 meters per second. Both have a mass of 5. So I'm going to make this way positive just because it's normal for me. And we can do it. So I'm going to start with momentum initial equals momentum final. So 5 times 3, right, that's initial momentum of this one, plus 5 times negative 8, right, momentum of this one, equals 5 times, we don't need that, VA plus 5 times VB. Right? We don't know what those are. These are actually the final velocities A and B, but we don't need the right final because the initial ones we already know. This is 15 minus 40 equals 5 VA plus 5 VB. I can simplify even more. This is by dividing by 5, and this is going to be negative 5 equals VA plus VB. Alright, so I also know that kinetic energy initial equals kinetic energy final. Right? So I have 1/2 times 5 times 3 squared plus 1/2 times 5 times negative 8 squared equals 1/2 times 5 VA squared plus 1/2 5 VB squared. Now, I'm smart, so I'm going to cancel out the 1/2 and the 5, giving me 9 plus 64 equals VA squared plus VB squared. And I just have two equations with two unknowns. Okay, so I can substitute. So let's say that VA is equal to negative 5 minus VB. So this is 73 equals negative 5 minus VB squared plus VB squared. 73 equals 25 plus 10 VB, right, just expanding this out, plus VB squared plus VB squared. And this whole part, that's like the expansion of that that squared. So then this becomes 73 equals 25 plus 10 VB plus 2 VB squared. And I can get this into a form. So 0 equals VB 2 VB squared plus 10 VB that's not very clear. Two VB squared plus 10 10 VB minus It's gonna take me forever if I don't write better. Minus 48. Okay. Divide it all by 2 to make it a little bit easier, and I've got VB squared plus 5 minus 24. And you can actually factor this. And a lot of times I will make these problems, especially if you have to do it by hand, easily factorable. This becomes 0 equals VB minus 3 times VB plus 8, which means that VB is equal to 3 or negative 8. Now, you always get two answers from this. It's pretty much guaranteed. Two answers. One of those answers, right, VB's initial velocity, this is actually V initial B. Okay? So you should always get the initial velocity as one of your answers. If you didn't, you made a math mistake. Okay? The other answer is not right either. That's V initial B, which means that the other one is V final B, which means we can then find that VA final is going to be negative 5 minus 3 or negative 8. Okay? Now, the second thing interesting about this is anytime you have two objects that experience an elastic collision, I didn't even say this was elastic. How am I? This is all dumb. Collides elastically. Okay? Anytime you have two objects that have the same mass that collide head-on, all right, that guarantees that they will swap velocities. Okay, every time. Don't have to do the math. Same mass, swap velocities. The closest example of something like this that you've seen, because elastic collisions are pretty rare, is like somebody hits a pool ball where the cue ball hits the other ball, and the cue ball basically stops. So another ball keeps going at like the normal velocity. That's basically the same situation. It's actually not quite elastic because there's some other things going on, but it's pretty close. Okay. All right. Am I recording? I think I'm recording. Yeah, I'm recording. Okay. I just want to make sure. That would have been really sad if I'd gone through this. All right. Okay. Another example of a pretty close to elastic collision is when a satellite does a gravitational slingshot around a planet or a moon. Okay. And so the reason why this is pretty close to elastic is because in a collision you lose kinetic energy when things like sound, light, heat, those sort of things. As long as the satellite stays outside the planet's what's it called? The planet's atmosphere, or if there's no atmosphere, then there's no friction, there's no air resistance, so it becomes pretty close to an elastic collision. Now, same idea. Potential energy initial equals potential energy final. All right, we've got our satellite, we got our mass of the planet, mass of the moon times velocity of the moon, which is 1,000, plus 1,000 times negative 5,000 equals mass of the moon times V final of the moon, right? And I guess I need to write plus 1,000 times V final satellite. Okay? And then I have the kinetic energy one too. I'm going to go ahead and cancel out the 1/2s, right? We don't need them. So I've got mass of the moon times 1,000 squared. And I know that I know the mass of the moon. I just didn't want to write 1e24 a bunch of times. It's confusing when I write that. Plus 1,000 times 5,000 squared equals 1/2, right? Mass of the moon times V final moon squared plus, oops, no 1/2. Told you we weren't going to include those because it's all multiplied by that anyways. Plus 1,000 times V final satellite squared. Now, this is going to be complicated to plug in, to do. The math, the actual like substitution of this is pretty painful. So I can type it in here. and you'll actually see I'm going to type these two equations in. And I guess I've already done it. Equations, so right there. I typed the two equations in. There's my momentum equation, mass, velocity of moon, mass of moon, velocity of satellite, mass of satellite. X is my velocity of the moon. Y is the velocity of the satellite after the slingshot. And I do the same thing with the kinetic energy equation. I scroll down, and you can see I got two answers here. And I can get the approximate forms, more digits here. One of my answers is 1,000 and negative 5,000. That means I've entered it right, because those are the initial values. Okay? The other answer here, right, is 999.99999, which basically means the moon didn't slow down at all. It's like basically didn't slow down at all. And the velocity of the satellite is now 7,000. So it's changed direction, but it's sped up by, its speed is increased by 2,000 meters per second. Now, it might seem like a lot of way to go out of your way to pick up some speed, but imagine if you wanted to get to like Neptune, right? Neptune is way out there. So going out, detouring around Venus or Mars in order to get faster speed is totally worth it, because you're only increasing your distance by a small percentage, because those are so much closer than Neptune is, or Uranus. Okay. All right. What about in 2 dimensions? Hey, collision's not head-on, like they're coming at different angles. Momentum's a vector, so both magnitude and direction are conserved. So you need to conserve both x and y directions. Okay. So look at an example of that. Got a 10 kilogram block sliding north, 5 kilogram block sliding east, and they collide perfectly inelastically. That means they stick together, right? So now we do PIX equals PFX, right? So initially in the x direction, we've got 5 times 20 plus 0 times 10, other way around, 10 times 0. That makes it clear that I'm putting the mass first. 10 times 0, and that's equal to, they stick together, so 15 times v final x. V final x is going to be 6.67 meters per second. Do the same thing in the y direction. P initial, momentum initial y equals momentum final y. Do the same thing. We've got 5 times 0 plus 10 times 5 equals 15 times v final y. V final y equals 3.33. And then you have to put them into a triangle, right? So we get the triangle is v final x, v final y, and we end up getting, when we do the Pythagorean theorem, you get v final is 7.45, and then the angle is 26.6 degrees north of east. Okay. All right, final one here. This is an elastic collision in 2 dimensions. So 1 kilogram ball, this is moving at 10 meters per second. And afterwards, it bounces off, they bounce off at angles. I want to know what the final velocity of each ball is and what direction they're going in. A lot of math. I'm not going to work it all out for you, but I want to show you the idea, right? So in this case, it's P initial x, momentum initial x, momentum initial y, or momentum final x. Ooh, it's very different. Initial y is definitely not what I want there. Okay. So how would I do that? Well, I've got 1 times 10 plus right, the red ball is not moving, so 0 is equal to 1 times v final, or I actually won't use final because we know we're dealing with finals here. So I'm going to use VA. I guess I'll maybe leave my green ball A and my red ball blue, or red ball B. VA, and this is going to be cosine of 37 degrees plus 1 VB cosine of theta, right? And then, oh, we do it in the y direction too. P initial y equals P final y. So I've got 0. There's no initial momentum in the vertical direction. is equal to 1 VA sine of 37 plus 1 VB sine of theta. And finally, we have kinetic energy initial equals kinetic energy final. So this is 1/2 times 1 times 10 squared plus 1/2 times 1 times 0 squared. That's equal to 1/2 1 VA squared plus 1/2 1 VB squared. Okay, 3 equations, 3 unknowns. I don't know VA, I don't know VB, and I don't know theta. I'm not going to solve it out here. It turns out this one's kind of like works out nicely that VA turns out to be about 8. It's actually 7.99, and VB equals 6.01. Right, because it actually turns out to be pretty close to a 10-6-8 or 6-8-10 triangle, which is a 37 53-degree angle. Okay, all right, that's it. I know it's a bit of a speed run, but that's the basic idea. Okay, all right.